Greetings all. In this little video, as the title indicates, I'm going to do some more work with a double integral related to either the mass or the center of mass for a planar lamina. And if you haven't realized this or noticed this yet in the previous double integral related videos, I'm actually more interested at this time in, can you set up the integration that measures something physically? Nearly everyone will say in the room, you're some sort of an engineering or science or computer science major, technology might be available to evaluate with a high degree of accuracy, but evaluate what? If you can't set it up, the computer can't deal with it. So this is another example of just emphasizing the can you set it up aspect of it. And I'll focus on a planar lamina example while I'm doing it. So I have a region of integration to play with. And this integral region is bounded by the graphs y equals e to the negative x and y equals e and x equals 0. We'll get to the density momentarily. If we were to rough sketch this region, x-axis, y-axis, e to the negative x looks a lot like this. The x-axis, the positive x-axis, is horizontal asymptote. It increases quite quickly to the left. It intersects the y-axis at the point 0, 1. E to the 0 power will be 1. It's the e to the x function reflected in the y-axis. X equals 0 is the y-axis. Those two graphs do not completely bound a region, but y equals e is a horizontal line. Y equals e. We now have a region of integration, completely bounded by those graphs. Now, if we were to set up this region of integration, eventually what we're going to do is find the moment about the y-axis, So that moment about the y-axis is the double integral of the density function over this particular region multiplied by, if you recall, x. Moment about the y-axis is indicating how things are balanced between the right and left side. I would expect this to be a negative number because the entire region is to the left side. Let's find out. Hopefully it will. Now, I certainly have the density function, and that part's easy to set up, but we could be looking at the region here as well. And I'm going to do this a couple of different ways because part of my main objective here is practicing setting up double integrals where regions of integration are different from previous examples. Even though this is a pretty basic function in a pre-calculus world, we haven't done much with it in recent video instruction. So let's see what we can do. If I were to look at it from a left to right sense, left to right, let's see here. The left boundary is, I have to determine what that is, and the right boundary would be 0. So that'd be x equals 0, x equals question mark we have to find. And the lower boundary and the upper boundary, well, the lower boundary is my function. If I were to set up my rectangle like this, the lower boundary is the function, so that's y equals e to the negative x. And the upper boundary is also a function. It's the horizontal line, y equals e. So if I were to set up this double integral in what I would call my native language, functions are in terms of y, so dy dx would be here, then I could fill in several of the blanks. I know that in here the y boundary is e to the negative x and y goes to e, and if you've been around a lot, I'm a big fan of identifying that these are y equal boundaries, and these x equal boundaries have to be constants, and I know that ends at 0. Well, I guess I better figure out what's going on here. Where is that intersection point? Guess I need some scratch paper to do that. Let's see if I can't squeeze it in up here. E to the negative x is going to intersect e, so e to the negative x equals e, otherwise known as e to the negative x equals e to the first power. That means that negative x equals 1, so x equals negative 1. Aha! There's that value. X equals negative 1. If we were to go and substitute these into this expression here, so the density times x, we might be able to evaluate it. But I would like to try switching the order. And I'll be honest right now, I'm doing it for fun. I like to see if I can do this. It's not always possible to do that switch, but we have seen that it may be that if you switch the order of integration, there are some advantages when actually integrating. And if there's an advantage of integrating by hand, you can probably guess it might be possible that the computer needs to do less work to get a more accurate solution as well. For those types of problems, fewer computations saves time. Let's see here. So we're going to switch the order of integration. So my y boundaries, lower to upper, the lowest y value is 1, and the highest y value is e. And then in the left to right sense, I'm using the same picture, forgive me for not taking time to draw up another one. It's kind of a rush order project, or you could say I'm being efficient with my space and time. From left to right, well, the left boundary is that curve, but I have to solve it for x equals. But the right boundary is the y-axis, and its equation I know, it's x equals 0. Let me just slide the paper up a little bit here. Low tech. So if y equals e to the negative x, and I want to solve it for x equals, natural log of y equals natural log of e to the negative x, natural log of y equals negative x, because those are inverses that undo each other, that base e logarithm. So therefore x equals negative natural log of y, and voila, negative natural log of y goes right there. So we're going to take these boundaries and put them into my moment about the y-axis, and I'm actually going to integrate that. So let me just do a little bit of scrolling here. Okay, that will work. I think I only need to see this much actually. So moment about the y-axis is the x value multiplied by the density function, which is some constant over y. We are going for a dx dy problem. How come? Teachers seem to be bored and want to torture us. So I know that these are my x equal boundaries here, and these are my y equal boundaries. And this last integral has to be constants. And I can see them here from 1 to e. And x goes from negative natural log of y to 0. All right, the nice thing is this integration is actually not too difficult. Might even be better than the dy dx version. Cannot promise that. Like I said, you're suffering from the teacher's curiosity here. All right, constant k factors out. 1 to e. X is the variable, y is a constant, so we'll leave 1 over y here. And I get x squared over 2. And I know that x goes from negative natural log of y to 0. Well, if x is 0, this whole quantity is going to be 0. And if x is negative natural log of y, I'll square that. It will become positive. But beware. Let's scroll again. 1 to e, 1 over y. You plug in 0 minus negative natural log of y quantity squared over 2. And now this minus sign is still here. K 1 to e negative natural log of y squared over 2 and over y. I guess I could factor the constant 2 out. Now, I'm going to do this part a little bit quickly, but remember you have this thing called a pause button, which could let you slow it down and think about it. But if you try a substitution with the substitute is the natural log of y, the differential for that, or the du for that, is going to be 1 over y dy, and I happen to have a 1 over y dy, and when I integrate u squared, I'm going to get u cubed over 3. I'm going to write that more quickly than you want me to, but remember you have a pause button. Let's factor out that 2. It's going to be natural log of y cubed over 3, and y goes from 1 to e. We're so close to finish now. So close to being finished. If y equals e, natural log of e is 1. 1 cubed is still 1. 1/3 times k over 2. What is that going to be? K over 6. If y equals 1, natural log of 1 is 0. So that term will be gone. Do you guys see it? Let me rephrase that. Do you not see it? There's something missing. I carelessly lost my minus sign. This is the moment about the y-axis, and it's negative because this particular region is entirely on the left side of the y-axis. So of course the part of the moment that's separating left and right is going to come out to be negative. If you find the mass and the moment about the x-axis and combine those three pieces of information, you can find the actual coordinates for the center of mass in this particular unusual region. All right, fun stuff. Well, until next time, I hope you have a good one.